An eraser. Today, the subject is the law of cosines. We'll get to that in a minute. It does sound kind of good. We had the law of sines. We have the law of cosines. It sounds kind of copacetic, symmetric. There will be no law of tangents, or cotangents, or secants, or cosecants. But, so let's go back a little. The goal we have here is, given some information about a triangle, given 3 pieces of information, we want to be able to solve the triangle. That is, find the other parts. So I look at this through the lens of the triangle congruences we talked about, SSS, SAS, ASA, which again is the same as AAS, pretty much, once you find the missing angle. HL, and then there's kind of a non-congruence, but it's still useful for us to look at, which is SSA. You may recall with SSA, sometimes you get a triangle, sometimes you get 2 triangles, sometimes you get no triangles. So we want to be able to deal with all these situations. I think HL mostly is taken care of by the Pythagorean theorem. Pythagorean. That's one of our tools. I guess I should write these down. Pythagorean theorem. We have the trigonometric functions, sine, cosine, tangent, etc. And on Monday we learned the law of sines. We learned about it, which says in a triangle with angles A, B, and C, and opposite side lengths in lowercase a, b, and c, that you have these nice ratios, sine of angle A over the length of the opposite side A is the sine of the angle B over B equals sine angle C over C. So those are the tools we have. ASA and AAS will succumb to the law of sines. As I said, Pythagorean theorem and the trig functions help with HL. SSA, again, law of sines is kind of our best bet. But we have these other 2 situations that we still don't know what to do with yet. I just see some new faces that I want to give full credit to. Okay. Notes are always useful when you can find them. There we go. Okay, so let me just put up 2 problems that we will get to. The first one is, what if we know three sides of a triangle? Let's say 5, 6, and 7. Okay, this is an SSS. We look at this and we look what we know, and we realize there's something missing, right? I mean, the law of signs will not help us because we don't have a complete ratio here. We know the sine of A over A will be the sine of B over B sine C. We don't have any angles, so that's not going to help. The second problem we're going to look at is, what if I have two sides and their included angle? This is an SAS problem. Well, we do have an angle, but we don't have this nice convenience with ASA and AAS where we can find the third angle. So we're just stuck with one angle. If we look at the law of sines, we don't have a complete ratio here. We know the sine of 38 over its opposite side will equal sine of one of these angles over their opposite sides. But we have two missing pieces of information. So we're stuck. So that's where the law of cosines comes in. Let's take a look at how we derive this. We start with just a general triangle. Again, I'm going to label the angles in the usual way and the sides. And I'm going to do something we often do. I'm going to drop an altitude from the C angle, and I'm going to call the length of that altitude H for height. And I'm going to use the point where the altitude meets the opposite side to divide it into two pieces. And I'm going to call one of the pieces x. But of course, if this distance here is x, the length of the triangle is c, so the other piece is going to be c minus x. This is the setup. I also want to make note of the fact that I have a relationship between h, b, and angle A here. I can clearly see that cosine of angle A is h over b, or if you like, h is equal to b times the cosine of angle A. Right? I'm going to use this later, but now we get to the guts of this. We take a look here, and we have two right triangles, and we're going to apply the Pythagorean theorem to both of them. So that's pretty straightforward. Over here we have b squared is going to equal x squared plus h squared. Right? Two legs of my triangle. And on the other side, we're going to have a squared equals, now we have c minus x squared plus h squared. Okay, so we have two equations, but we have far too many variables. So we want to cut down on variables. See immediately that there's an h squared in both of these. So probably the thing to do is solve for h squared and use it as a substitution. So I have h squared equals b squared minus x squared over here. And now I'm going to just plug this in to this equation. A squared equals c minus x squared plus b squared minus x squared. Okay, let's multiply this out. So we get a squared equals c squared minus 2xc plus x squared plus b squared minus x squared. Okay, that's excellent, because now I'm getting rid of my x squareds here, right? So I'm pretty close to what I want. I have a squared equals c squared minus 2xc plus b squared. Now I just have this pesky x to deal with, but now I go back to where I started. I find I did something wrong. What did I do wrong? Let's try this again. Putting the wrong variable. X over b is the cosine of angle A. So x equals b cosine of angle A. All right. Now that's useful. Now I can get rid of this x. So I get a squared equals c squared minus 2bc cosine angle A plus b squared. Okay, now that's not the right form I want to leave you with, but that's our basic law of cosines. Let me just rearrange this a little here. A squared equals c squared plus b squared minus 2bc cosine angle A. And it's worth noting that the way I've labeled these is completely arbitrary, A, B, and C. And so I'm going to, again, arrange this the way you're more likely to see it. I'm going to write it as c squared equals a squared plus b squared minus 2ab cosine angle C. The reason I like this form a little better is it conforms with something else you know, the Pythagorean theorem. If I just eliminate this part, it does seem to be the Pythagorean theorem. Okay. So rather than trying to remember the whole thing, you can remember, well, the Pythagorean theorem with an adjustment here. Minus 2ab cosine angle C. All right, let's investigate this a little bit now. What would happen if I had a right triangle with the right angle being angle C? So my angle C, my A and my B. What happens? Well, I get c squared equals a squared plus b squared minus 2ab cosine angle C. What's the cosine of 90 degrees? 0. Right? So in fact, just as we hoped, when I have a right triangle, the law of cosines just becomes the Pythagorean theorem. something else you might have noticed here is, except for the cosine C part, this looks a lot like one of our patterns, doesn't it? Well, actually, two of our patterns. If cosine of angle C were 1, then this would be C squared equals A minus B squared. And if cosine of angle C were minus 1, this would just be C squared equals A plus B squared. Let's think about what that means. Where is the cosine 1? What angle would have the cosine 1? 0. Okay. How about the cosine minus 1?
180.
180. All right. Well, let's think about that. That doesn't sound like a triangle, having a 0 angle or 180. But if you think of a triangle where A and B are kind of collapsed down to where they just sit on top of C. In other words, this angle here gets bigger and bigger until it's 180. Well, now this statement makes perfect sense, right? Because C is equal to A plus B. So, of course, C squared will equal A plus B squared. What would a 0-degree angle look like between A and B? Well, there's A and there's B, and we let this angle get smaller and smaller until it's 0. So here you have A, and here you have B. But then C, the third leg, is this piece here. Well, again, it makes sense, because now, well, it doesn't really matter whether it's A minus B, does it? Like in my example, A minus B would be negative, but we're squaring it. So I guess it's important we're squaring it. B minus A squared is equal to C squared. So in the limiting cases, we can see that this formula works. All right. That's not going to come up very often. Give this a label here. This is the law of cosines. Let's see if we can apply it to a more typical problem. Let's look at what we have over there. 5, 6, and 7. Okay. And maybe I should give these some labels, these angles, these vertices. Okay, how would I use this? Well, let's see. C squared, that would be 7 squared, equals B squared, that would be 6 squared, plus A squared, that would be 5 squared, minus 2BC cosine angle C. Minus 2 times 5 times 6 cosine angle C. So the only unknown here now is cosine angle C, or if you like, angle C. So I can solve for this. My cosine of angle C would be 7 squared, I guess I'll just do multiplication. Easy. 49 minus 6 squared minus 5 squared divided by minus 2 times 5 times 6. that's minus 60. Okay. What's this? 50, 61. So 49 minus 61 is 60, no, 60, 61 minus 49. It's minus 12 over minus 60, or 1/5. So my angle C will be the inverse cosine of 1/5. Okay, does that make sense? Let's take a look. The inverse cosine of 1 divided by 5, that's about 78.5 degrees. 78.5 degrees. Okay. So we cracked this nut here, the SSA. I'm sorry, the SSS. We're not quite done. We have 2 more angles to find. But now we have some choices about how we go about this. Right? We've got an angle and an opposite side. So we have that important ratio to use the law of sines. We could use that against these sides and these angles. Or I could repeat what I just did using the law of cosines, but using a different angle as the one with the cosine. And then finally, once I find 2 angles, I don't have to go through all that trouble. I just realize they add up to 180. So SSS succumbs to the law of cosines. That's nice. Now we, or you, can solve all those triangles. Yes?
For the formula, shouldn't it be A or?
Yeah, I usually make at least one mistake here. Yeah. AB. Is that it?
Yeah.
Okay. I plugged in the right numbers, though, didn't I?
Yeah.
Thank you. It's in my contract. I have to make at least one mistake like that. If I make 2, I get a bonus. Okay. Yay. We can solve SSS. What about SAS? Okay. Got a nice looking problem here. Okay. 20 degrees, 38, 6 and 8. Well, let's call this C. Little C, little A, little B. So let's try and find C here, all right? C squared, again, A squared plus B squared minus 2AB cosine angle C. So I have all these values. This is 36. B squared is 64 minus 2 times 48 times the cosine of angle C. That's C squared. Or C is equal to the square root of, what's this, 100 minus 96 cosine C. Which is 38 degrees. Okay, I'm gonna solve this with a calculator, but I want to make a comment. When you do the homework, if it asks for the solution, you should probably go ahead and do this. But when it comes to an exam, you know, you might come in with a nice calculator, and you might be able to do this. get the approximate value. But if you were to leave it just like this, I would be perfectly happy. Especially on an exam, as long as you show me you know the formula, you don't actually have to come up with the actual number. Okay, 100. Or you don't like this. I don't like that. Well, we'll find out. 100 minus 96 cosine 32. Oh, okay. And I find the square root. And I get approximately 4.31. Right. Another nutcrack here. SAS of cosines. Now again, I'm not done. I'm missing two angles. But again, I have some choices here. Right? I have a ratio, sine of 38 over 4.31, in the law of sines. So I can use that for either of these angles to find their angles by finding their sine. I likewise, since I have side, side, side now, I could just use the law of cosines again. So you can kind of fill in those pieces. All right, any questions about this so far? See, right now, we have kind of the whole spectrum here. I want to go over one part of this first. I want to remind you about this SSA situation here. Recall, this is not a congruence, so there's no guarantee about what you get here, but there are things we can do. You'll recall that if you have an angle and two sides, that there are a few different possibilities. One possibility is that there's a solution, but there's actually two solutions. In other words, you could have an angle here, but its complement could also be a solution. So you could get two triangles out of this. You could get a right triangle. Okay? Here's an angle, you have a hypotenuse and a leg. So here you're only going to get one solution. You could get an impossible situation. You could get that your second side is just too short. It's just kind of dangling here, and you don't get a triangle. So you could get zero solutions. I think I mentioned all this on Monday. There's one more possibility I didn't mention. I should have. If your second side, let's call this A and B, if B is greater than A, right, you're not going to have this kind of weird situation where you have two, right, two possible triangles. If B is greater than A, then swinging B over doesn't give you a triangle if this is an angle. So in the case that B is greater than A, you get a solution, but you just get one solution. So there are two ways you can end up with just one solution. So that pretty much covers solving triangles. That's not all we're going to do with trigonometry. There's a lot of other neat things to be done. But this is kind of the heart of what we're heading for. I like to think of it as we're extending geometry a little. So in geometry, we could do just so much with triangles, but now with the trig functions and these other relationships, we pretty much know as much as we can about the triangle. I'm going to do a few more examples. And I want to show you a few more, we'll call them gotchas, right? First, let's just do a side problem. Let's say our sides are 10, 15, and 30. No, well, that's not going to work. 10, 25, and 30. So how would I go about finding an angle for this triangle? What would I use? Well, cosines, okay. I'll give you some labels here. Someone like to guide me through how I would use the law of cosines here? Kind of hot in here. Can we open a window? Yeah, thank you. How would I go about this? Yes?
Side, side, side.
Well, it is side, 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 but we're going to use the law of cosines, right?
Yeah.
So how would I apply that here? Be brave. Somebody. Jessica?
So the setup would be 10 squared equals 25 squared.
You're doing just what I want, but a little slower. 10 squared equals
25 squared
25 squared
plus 30 squared
plus 30 squared
minus 2 times 25. Yeah, 30 times
cosine of which angle?
C.
B.
No, C.
Okay. Did I do something stupid?
I think she said C. I think she said C.
Oh, you said C. Oh. You said C? Thank you. Okay. So let me solve for angle C without doing much else. Cosine angle C equals, well, 100 minus 225. No, that's not 225. What's 25 squared? If you're going to be computer science majors, you should know your squares. Minus 900 over minus 2 times 25 times 30. Okay, or the angle C is just the inverse cosine of that value. Again, minus 50 times 30 is 150. All right. That's a perfectly fine answer if we don't actually need the value. But since we're going to go on, I guess I should do that.
One question.
Yes.
Why is it inverse cosine?
Cosine C is this. So I take the inverse cosine of both sides. The inverse cosine of the cosine is angle C.
Oh, yeah. Okay.
So what do we get? We get 100 minus 625 minus 900 divided by minus 150. That looks problematic. What did I do wrong? Oh, 50 times 30 is not 150, it's 1500. 10. And the inverse cosine of that is 18.2 degrees. So which angle is that now? 60. So apparently my diagram here is in and out of whack. 18.2 would be a very small angle. All right, that's how we get started, and again, the rest is just either repeat for angle B and A, or use the law of sines. All right. Here's another problem I want you to take a look at, think about. About 10, 15, and 30. How would I go about, did you have a question? No. Okay. How would I go about solving this one? This one's a little different. Someone want to guide me through this one? A, B, and C. Some brave soul. Some really frightened soul, but who's willing to put it out there. Anybody wants to try? I mean, you'll get a chance when you work on the homework, of course. Alexis, do you want to try? No? It's a good thing this isn't the public speaking class, is it? All right, Phil, go ahead.
What if you do the thing with that H?
Well, I could, but I'm lazy. I just want to use the law of sines, law of cosines.
Can we do that though?
Yeah, I've got 3 sides. Yeah, that's what we just did.
And you said it's special.
It is. It is. Yes. Let's go. Come on.
So,
Give it a try.
30 squared. 10 squared plus 18 squared plus or minus 2 times 18 times 10 times 4 times 30. Oh wait, C.
See. Okay. Good. All right. All right. Let's jump here to what we want. It's 30. I might as well write it 30 squared because I'm not gonna square 18. I'm not that smart. Over minus 2 times 18 times 10. Okay, so I just want for the angle, I want the inverse of this. Okay, everyone who has a calculator, take out your calculator and then you're good at this. Plug these numbers in. You want to take 30 squared minus 10 squared minus 18 squared divided by minus 2 times 18 times 10, and then finding inverse cosine of that. So who wins the button pushing race here? Anybody get this yet? Domain error. Yes. Well, let's back up a little. What's 30 squared minus 10 squared? What is that? That's 900 minus 100 minus 18 squared. These things really make us stupid, but that's okay. Divided by minus 360. Okay, so I get minus 1.32. So here I get the inverse cosine of minus 1.32. All right. What went wrong? Well, you can't have the cosine of an angle be minus 1.32, right? What's the domain of the inverse cosine function? Or, if you like, what's the range of the cosine function? The range of the cosine is not all positive numbers. That's the domain of the cosine. I heard someone else. Yes?
Negative 1 to 1.
Negative 1 to 1. This is outside the domain. Oh. Well, that's weird. We've got a triangle and it's not working. What's wrong here? Well, now let's take a little closer look at this triangle here. Is this a triangle at all? 10 plus 18 is 28. I mean, I drew it this way, but the sum of these two sides is less than this. Right? So the pearl of wisdom here is, just because I draw something and I put numbers on it, that doesn't mean it's a possible triangle, right? Let's do one more of these, where we pretty much expecting trouble. The triangle has a 60-degree angle. This side is 10, and this other side is I guess I'm drawing it a little funny here, is 8. Will that do? Yeah, okay. So how do I go about solving this triangle? This is that weird one, SSA, so we're already looking at this closely. What am I going to use to try and solve this triangle? Yes? Law of sines, okay. Sounds like a good idea. So here's my little b, here's my little a, c. So law of sines tells me that sine of 60 degrees over 8 will equal what? The sine of b, angle b, over 10, right? Okay. So the sine angle B will equal 10 times the sine of 60 degrees over 8. We all know the sine of 60 degrees, don't we? We all can figure it out, can't we? What's the sine of 60 degrees? Yeah. 10 times the square root of 3 over 2 over 8. Okay. So let's find the inverse sine of, well, that's going to be 5 square root of 3 over 8. All right, let's try that. What happens? Happened again, didn't it? If you didn't do this in your calculator and you're sitting next to somebody, look over on their calculator so you know what it looks like when you have a domain error. It says error domain, right? Well, what went wrong? Well, again, what's 5 times the square root of 3 divided by 8? Quit first. 5 times the square root of 3 divided by 8. Oh, I'm trying to find the sine, the inverse sine of 1.08. Well, that's not going to work either, right? So what does that tell me about this triangle? Well, if I get out my ruler and I draw this a little more carefully, I'll see that if I have a side of 8 and an angle of 60, at 8, a side of 10, this 8 doesn't quite come down to hit this side of the triangle. So it's not a triangle at all. So you have to be aware of these gotchas, shall we call them. Otherwise, we've kind of done it. We've solved triangles. Yes?
It gives the same result, but I just want to say that it's 5 times over 4.
I'm sorry?
It's over 4, not over 8. On the last bottom part. I don't know.
I'm just looking at the 60, 90. Okay, you're saying... I want to find my error. Sine of 60 over 8 should be the sine of this angle, let's call it alpha, right? Sine of alpha over 10, right? So where's my mistake?
I'll be bad on the last line. It's 5 times square root of 3 divided by 8, and it's supposed to be divided by 4.
I keep hearing that, but isn't 10 times the square root of 3 over 2 5 times the square root of 3?
Yeah.
Oh, I don't get my bonus. Something happened here? Oh well. There's this phenomenon that seems to be prevalent. It's Murphy's Law, but I usually do a better job in this. I think I do a better job in the second class, but then the video doesn't. Something goes wrong with the video. All right. Okay. That's it for triangles. I'll put up the assignment. I think it may already be up, but I'll put up the assignment for this. Work with these, learn how to do them. Right? Ask questions if there are any of the problems you have trouble with, or come to office hours. We will move on to the next next fun topic.